and we are going to study module number 6. In module number 6, we was having the Murray model. So in the Murray model, state will be represented with state name. This is the only difference with the Millet machine. So here we represent with the output. So here the state will be represented with the output, and we will start with one example. Like if you want to design a Murray machine for 1001, so in that first we have to start with a state diagram. So we will draw the state diagram and then we will see the complete procedure, how we can draw the circuit for the Murray machine. So state diagram for 1001. So as you know, we have to initialize with an initial state A and output will be 0. This is the representation of a state with output. As this is the initial state, we have not received any correct pattern till now. So my output is 0. Whenever I will receive first bit correct, that is 1 for us, I will move to the another state, that is B, and I will write down like B by 0. Here at the center, I will write down the input. In the Millet machine, we was writing like A, and here in between two states, we was writing the input by output. Whereas in the Murray machine, this was the Millet machine. Whereas in case of Murray machine, we represent states with the output. So now, if I will receive the second bit 0, I will move to the another state, that is C. And as we have not received the correct bit pattern till now, so output is 0. After that, if I will receive the another bit correct, that is 0, I will move to the another state, that is D, and output is 0. And when I receive the last bit correct, that is 1, my output will be 0, that is E by 0. So this is all about the correct bit pattern. Now, if you are in the state A, that means we are in the initial state. And if you are getting continuously 0, that means we are remain in the same state because we have not received any bit correct from the pattern. So it is like 0 in the same state. If you are getting 0, 0, 0, we have not received any bit correct till now. So it is what? Same state. Now, if you are in the state B, that means I have a single bit correct, that is 1, and I was waiting for 0. If I will get 0, I will move to the another state C. But what will happen if I am getting continuously 1, 1, 1? At this scenario, we have at least one bit correct, and I will remain in the state B because this is the single bit correct state. Now, if you are in the state C, that means we have 2 bit correct, that is 1, 0. And after this, if I will get 0, I will move to the another state. But if I will get 1, what will happen? In this scenario, we have only single bit correct, that is 1, right? This is 1. That means I have to move to the single bit correct state, that is B. Now, if you are in the state D, that means I already received 1, 0, 0 as a correct bit, and I was waiting for 1. If I will get 1, I will move to the state E. But if I will get 0, that means there is a complete loss of pattern, and I have to come back to the initial state, that is A, and I will write down here 0. Now you are in state E, then you have to think whether it's a overlapping pattern or a non-overlapping pattern. So first time I am doing for the overlapping. So if it is the overlapping, you have to check how many bits can be in overlap. If I write 1, 0, 0, 1, 0, 0, 1, there is a chance of a single bit overlap. And as in the Murray machine, you have to skip 1 plus number of intersection bits or that are overlapping bits. So here we have one overlapping bit plus one. So we have to skip two states. So from E, I will come to 0. I will come to C whenever I will get 0. Now, if you are in the state E, if you are in state E and you are getting 1, so here I already received 1001, and if I will get 1, then I have to wait for how many bits? 3 bits. That means we have single bit correct. So single bit correct state is what? B. So I will move to state B, and here I will write down 1. So this is the state diagram for 1001 overlapping. Clear? Note down this one, then I will tell you how to construct the state table. Because the state table is again an important part. This is the first step, that is the drawing of the state diagram. Then I will tell you the state table. So here for the state table, we require this state diagram. So here to construct the state table, in the state table, as you know, we have present state. Then we write down input, that is represented by X. Next state, then we write down Z, and then we will use certain flip-flop to design the circuit. So here I'm considering how many states are there. We have 5 states. Okay. So here I am writing A. This is B, C, D, and E. That is E. And X can be 0, 1, 0, 1, 0, 1, 0, 1, and 0, 1. Now we have to check the next state. If you are in the state A and you are getting 0, so you will remain in the same state, that is A. And if you get 1, you will move to the next state B. So here it is A and this is B. Similarly, if you are in state B and you are getting 0 and 1, so you will move to the either C state or B state. Now, if you are in state C and you get 0, so you will move to the D state. If you get 1, then you move to the B. So this is B state. Similarly, this will be A state, E state, and this is C and B state. Now, output is 1 for two condition, because as you know, output is fixed with the state. It is 1 for two condition when E is moving when the state is moving from E to C or E to B. So C and B both are 1 1 here. E to C or E to B are 1 1. Rest all others will be 0. So I am writing 0 0 0 0. This is also 0 0 0 0. So in case of Moore machine, we have two state output 1. That means output is 1 for the two conditions. When you are moving from E to C, because output is fixed here, and similarly when you are moving from E to B, then also your output is 1. So in the Moore machine, you will get output 1 in two conditions. Now here we have, as you know, that ABCD is the alphabet, and that we can not use in the digital design. So here we will use some binary encoded bits. So as we are having the 5 states, how many minimum bits are required to encode? We require 3 bits. So that's why I'm taking as A is as 0 0 0 0 0 0. B as 0 0 1 0 0 1. C as 0 1 0 0 1 0. This is 0 1 1 0 1 1, and this will be 1 0 0. This is 1 0 0. Clear? As we was having the 5 states or 5 combination of 5 states, we cannot represent by 2 bits, because with the 2 bits we can represent only 4 states. So here we have considered 3 bits to encode the states. A is represented by 0 0 0, B is represented by 0 0 1, C is represented by 0 1 0, B is represented by 0 0 1, D is represented by 0 1 1, B is represented by 0 0 1, A is represented by 0 0 0, E is represented by 1 0 0, C is represented by 0 1 0, and B is represented by 0 0 1. Is this clear? So this is the state table. But now after that, we have to see which flip-flop we are going to use. For example, in this question, we are taking JK flip-flop to implement. If in the question they don't mention, you use D flip-flop because it is the easiest one. But as this is the numerical, and for example, they mention you have to use only JK flip-flop, then how you can do that? So JK flip-flop, if you are using JK flip-flop, for that we require the transition table. So transition table of JK flip-flop, I am writing it here. Qn and J and K. So this is 0 0 1 1 0 1 0 1. This is 0 1 don't care 0 1 don't care. So this is the transition table, the excitation table of JK flip-flop that we have to use to find out the values. So what value we need to find out here? So here we require the value of J2, K2, J1, K1, J0, K0. That many values we required. And how to find out this one? Assume this is Q2, this is Q1, this is Q0. Similarly, this is Q2 plus 1, this is Q1 plus 1, this is Q0 plus 1. Just to tell that this is the present state and this is my next state. So now you compare Q2 and Q2 plus 1 based on the excitation table of JK flip-flop. So this is the excitation table of JK flip-flop that we are using to find out the value of J and K. So if you compare it, you will get 0 0, don't care here. This is 0 don't care, 0 don't care. If it is 0 0 0 0, so for 0 0 you see this is 0 0 condition, and J value and K value is 0 don't care. Okay, so if this is 0, this is also 0, you will get 0 don't care, right? Similarly, this is 0, this is also 0, so 0 don't care. Similarly, this is 0, this is 0, so 0 don't care. Similarly, this is 0, this is 0, so 0 don't care. Now this is 0, this is 0, 0 don't care. This is 0, this is also 0, so 0 don't care. This is 0, this is 0, so 0 don't care. This is 0 and this is 1, right? So this is 0 and 1. 0 1 condition says it is 0 1 don't care. So it is 1 0 1 condition. 0 1 condition is 1 don't care. 1 0 condition is don't care. 1 1 1 condition. Sorry. It is 0 0 condition, 0 1 condition. 0 1 condition is 1 don't care. 1 don't care, then don't care 1. And then if it is 1 0, for 1 0, it is don't care 1. So this is the value of J2 K2. Similarly, if you want to find out J1 K1, then in that case you compare Q1 and Q1 plus 1. So here, if you compare, this is 0 and this is 0, so you will get 0 don't care. This is 0 don't care again because this is 0 0. For 0 1, it is 1 don't care. This is 0 don't care. It is don't care 0. It is don't care 0. Now here it is don't care 0. This is also don't care 0. This is don't care 1. This is don't care 1. This is don't care 1. This is 1 don't care, and this is 0 don't care. So this is the value of your J1 K1. Similarly, I can find out the value of J0 and K0 by comparing Q0 and Q0 plus 1. So here the value that you will get will be 0 don't care, 1 don't care 1. This is don't care 0. This is 1 don't care 1, don't care 1, don't care 1, 0 don't care, and 1 don't care. So this is the complete state table. Everyone note down this one, then I will move to find out the expressions for J2, K2 and all. Any doubt in the state table? If you have, please ask. Anyone? Completed. Can we move to the another part? That is the K-map designing to find out the expression of J2, K2 and J1, K1. So if you want to find out J2, in that case, we require 4 variable K-map. Why? Because here we require Q2, Q1, and in this place we have Q0X. So here, as we are having Q2, Q1, Q0 and X, total 4 variables are there. That means we require 4 variable K-map. So I am drawing 4 variable K-map like this. And based on the value, if you fill, you will get a single one only at 0, 1, 1, 1. That means 7th bit will be 1. And after 7th bit, you have all the condition as don't care. Okay. So as you have only here also you can fill all other values are don't care, right? So till we have 9, we already know. After that also 9 to 15, 1, 1, 1, 1, all will be don't care. Okay. So it's not only ending in the 9. If you are moving onwards after 9 also 1001, and if you are moving till 1111, in that case these values you have to assume as don't care because we don't know anything about it. Okay. So that value you have to assume as a don't care. So after 7, all bits will be don't care. So after 7, I am making it as 8, 9, 10, 11, 12, 13, 14, 15. All will be don't care. Okay. So till here, till 9, we know the value. After 9, you have to assume is as a don't care condition. Okay. So after 9, you have to assume as a don't care. That's why we got this JK. And now we will make the group here. So here the group is what quad is not possible, only pair is possible. And if you draw the pair, then the expression for J2 that you will get will be Q1, Q0, X. Now similarly, I will draw for K2. For K2 also we require 4 variable K map like this. And here you see from here to here all are don't care. That means till 7 is don't care. So I'm drawing it directly. Till 7 is don't care. So don't care, don't care, don't care, don't care. Till 7, that means top most filled with the don't care condition. Now this is the 8th and 9th. This is 8 and this is 9. 8 and 9 are 1, 1. So 8 and 9 I am making as 1, 1. And after 9, we don't have values. That means it's a don't care condition. After 9, it's a don't care condition. So you have to fill again after this by the don't care values. This is don't care, don't care, don't care, don't care. don't care. So if this is the situation, tell me which type of group is possible. Octal or hexa 16 group is possible. Tell me anyone. The group of 16 is possible or a group of 8 is possible. Anyone? Is my voice is audible?
Yes.
Okay. So here we can make a group of 16 and that value that we will get is Q2 is equals to 1. Similarly, I will draw for J1. So J1 is also a 4 variable K map and I will draw it like this. This is Q2, this is Q1, this is Q0 and this is X. So from the value if I draw it is 2. So 2 is 1, 2 is 1 and after that all are the don't care condition till 7. So here is don't care and here is don't care 1, don't care, don't care, don't care, don't care, don't care. So this is the scenario that we are getting for J1. For J1 is 1 here, then don't care, don't care, don't care, then we have 1. So two ones are there that I filled it here. Now here we can make a group of one quad like this. One quad I will make it like this. And one quad I will make it like this. So here the expression of J1 will be given by J1 is equals to Q2 x bar plus Q naught x bar. So this is J1. Similarly, I have to find out the value of K1 now. So for K1, again, I will make a 4 variable K map like this. And based on the values, I am filling it here. The don't care 1, 1, 1. Then these are again a don't care condition after 9. So you can make it like this. Now, again, we have to make the group here. So one group, two octal we can make, one octal like this and one octal like this. So the expression of K1 will be given by X plus Q naught, and this is the expression of K1. Similarly, we have to draw the K map for J0. For J0, also I'm making the K map, and it will be 1, don't care, 1, 1, don't care, don't care. And this is 1, then don't care, don't care, don't care, don't care, don't care. And this is also a don't care condition. So if this is the scenario, we can again make a two octal here. And that octal will be like this. One octal, another octal like this. And the expression that you will get will be J0 is equals to X plus Q1. Similarly, we will make for K naught. So this is the value of K naught here. And for K naught also, it's 1, 1 here, and then all are my don't care condition. And no, sorry. All are don't care here. This is also a don't care condition. This is don't care condition. Only this don't cares. This is 1 here. This is 1 here. This is 1 here. Don't care, don't care. Like this. So here how we can make one. Okay, here we will make two octal. So here I am making one octal like this from the corner ones, and I am making another octal like this. So the expression that you will get for K naught will be given by X bar plus Q1. Similarly, we have to find out the expression of Z. Here we have to draw the K map because in Z we have two conditions where your output will be 1. That's why I am making the K map, and K map says the value of Z is 1 two times like this, one for 8, another for 9. So one for 8, another for 9. So here I am making it one is 8, another one is 9. After 9, here in Z, after 9, we don't know any values that we will assume as a don't care. So after this, we are assuming as a don't care condition after 9, and this is the value. If you make a grouping like this, you will get the expression of Z is equals to Q2. So now we have all the expressions. I'm writing it here and then I will make the circuit diagram. So J2 we receive as Q1, Q0, X. We receive K2 is equals to 1. We receive J1 equals to Q2 X bar plus Q0 X bar. We receive K1 is equals to X plus Q0. We received J0 equals to X plus Q1. Similarly, I received K naught equals to X bar plus Q1, and the value of Z that we receive is Q2. That many values we require to draw the circuit diagram. Now, how to draw the circuit diagram? Here, first you draw the JK second flip-flop. So here I am writing JK. In bracket, I am writing 2. After that, I will draw JK1 and then I will draw JK0. So the value of J2 is one AND gate is enough, right? One AND gate is enough for J2. So here I am making one AND gate and here I am providing it Q2, Q1, Q1, Q0 X, Q1, Q0 X. Similarly, uh, K2 is 1. So here I will make it K2 equals to 1. Now J1 is having the two AND gates. So first I will make a two AND gate like this, two AND gate. And then in parallel, I have to make one OR gate that I am giving as a, this is J2, this is J1. And the values is Q2 X bar. So this is Q2, this is X bar. And then Q0 X bar. So this is Q0 and this is X bar. This was the J1, and similarly K1 is what? OR gate. So I will make one OR gate here, and in these terminals I will provide X Q bar, X Q bar, Q0 is the input that we have given for the K1. Similarly, J0 is X plus Q1, so X plus Q1, X, this is X, this is Q1, this is J0, and K0 is X bar Q1. So again, I will use one OR gate and that will work as a 0, 1 not and directly. And here bar is given for X Q1. So this is X and this is Q1. So after this one, I will get the value of Q2. This is Q1 and this is Q0. And we have seen Z is equals to Q2. So directly we can make it like this is my Z. But before that, we have to provide the same clock to all the flip-flops. So that's why I'm giving it as a synchronous clock to all the flip-flop like this. And this is what a clock, CLK. So this was the Murray machine for 1001. And that's actually the end of your module number 6. Now we will see some miscellaneous type of question from different modules. So let's start with the fifth module because we have recently only completed fifth, sixth and seventh. So I think we should start from module number 5. So from module number